Hi, everybody. Welcome to Friday morning. Hope you're all doing okay. Today, we're going to be talking about polymer chemistry and how we talk about polymers, how we draw them, what they are, of course, and all of that. So if you're following along, as usual, feel free to ask questions in the chat or on Discord. If you're watching later, if you still ask me questions, of course, and I'll try to get back to you as best I can. The resources linked on polymer chemistry in the module are good references. I encourage you to read through them, look through them, but they do go a little bit more in depth, particularly that one link, than what I would require that you know for this class. So you can use this session today as a guide for what I expect you to be able to do. I'll try to be really clear about that. And if you're interested in other aspects of polymers, of course, feel free to read and do whatever research you want on that. All right, so let's take a look. So first of all, we should probably define what we're talking about here. In general, we can think of polymers as large molecules composed of or made of or synthesized by repeating small molecules. So what that means is, well, we'll see some examples, but basically you start with this small molecule, something with a couple carbon atoms or something like that, and that's called a monomer. So that's the small molecule. And then you just kind of connect it to itself a whole bunch of times and make a big molecule. So it's like, if you imagine a children's toy or like Legos or something. I'm not calling Legos children's toys. I know lots of people like Legos. But something like that, where you take one small piece and you just kind of keep connecting it over and over and over again until you make something very big. If you do that with molecules, you have what we call a polymer. So the monomer is that first little thing that you start with, and then the polymer is the large thing that you end up with after you've connected this thing to itself a bunch of times. Right. So let's look at an example of what that is chemically, and then we'll kind of talk about where we experience these or how you may know of some of these. So for one simple polymer, we'll take polyethylene. So we're going to take this molecule ethylene, which is just two carbon atoms connected by a double bond, and then two hydrogen atoms. So reviewing back a little bit to what we've talked about in the past, remember that carbon always wants to have 4 bonds. So if you have a double bond between two carbons, then you can have 2 hydrogens per each carbon. All right, so this molecule is called ethylene, sometimes ethene also. And what we can do with this molecule, it's a gas, and you can just take like a big tank of this stuff and subject it to some sort of a reactive chemical that's called an initiator. And the reason I'm being vague here is that there's lots of different possible initiators. There's ones that use radicals, which is a single electron source. There's acids, there's anions. There's various ways that you can initiate this reaction. But basically, you just kind of make this thing more reactive. You sort of break one of these bonds. And then all of these ethylene molecules in this big sample start linking up with each other. So you end up having still your CH2CH2, but now with a single bond here instead of a double bond. And if you have that single bond instead of a double bond, that means that these carbons now only have 3 bonds instead of the 4 that they would want. So to get those 4 that they want, they go out and connect with other ethylene molecules, and it makes a chain reaction that just goes on and on. So we can think of a polymer as these ethylene units repeating over and over again. And it could go on and on and on and on and on for a very, very long time. Many polymers have hundreds, thousands, 10,000s of monomer units all hooked together. So you're talking about this thing just connecting over and over and over and over and over again. And so the resulting polymer that you get from doing that connection is called polyethylene. So naming polymers is quite easy. You just take the name of the monomer and you put poly in front of it with parentheses. Sometimes for really common stuff, the parentheses end up getting dropped too. So it's just polyethylene as like one word. All right, so this is polyethylene. Polyethylene is a really common polymer. It's used in all kinds of applications, such as plastic bags are polyethylene. Some types of bottles, not pop bottles, but the kind of like squishier bottles, like milk jugs, shampoo or conditioner bottles that you can squeeze. Those are all polyethylene. A lot of carpet is polyethylene, and other kinds of like stain or water resistant fabrics. So that's this stuff. As you'll see throughout this, we're going to use the terms polymer and plastic somewhat interchangeably. Polymer is the chemical term as we defined earlier for this long chain. But many polymers are what we call plastics as materials, and that comes from the word thermoplastic, which describes something that can be reshaped by heating. So many of these polymers, including polyethylene, you can take it and you can melt it and then reform it, remold it into something else. And so that's how stuff is produced. Stuff is made out of polyethylene. Is you buy just like little beads or little balls of polyethylene in bulk. You put them in whatever your factory, melt them down, and make whatever you need to make out of it. So that's where that term plastic comes from. So most of the examples we're going to see today of different types of polymers are can also be described as plastics. All right. So we also want to be able to draw these in a couple different ways. So one thing we want to do is go back to our line structures from earlier in the semester. Because as we know, when we're drawing bigger and bigger things, it actually becomes easier to use line structures. So with ethylene, if we want to draw a line structure for that, remember, we don't show the carbons, we don't show the hydrogens, we just show ends of lines or double bonds. So ethylene as a line structure is just kind of two lines like that. And then if we draw the polymer of ethylene, we would take that same structure and connect it over and over again. So we have this. And one way you can do this, just to kind of see how it goes, is draw the thing over and over again first, and then do the connecting. So here's the drawing over and over again, and then we can do the connecting. And as you can see, this ends up just being kind of like a giant carbon chain that goes on and on. And that's what a line structure would look like. So that helps us to visualize it, because we can say, okay, a polyethylene chain is just going to be like this big floppy chain of single bonded carbons that goes on and on and on and on. Now, notice how we're not really specifying length here. We're just saying it just keeps going. And that's a fine way to do it. But the most efficient way to show that something is just going and going and going is to only express the repeat unit. So the smallest bit that expresses the monomer, and then show that it's repeating. So often when we draw a polymer, we want to kind of just take a look at the structure and just look for the smallest part that expresses what's really doing the repeating. So in this case, what I've highlighted here in parentheses, those are the two carbons that are really repeating over and over again from the monomer. So 1, 2, 1, 2, and then it just kind of keeps going 1, 2, 1, 2 as you go on throughout the chain. So another way to express this, in the way that you'll see it most often, is just that part. So we take the monomer, which in this case in a line structure is just a line like that. Then we draw it connecting kind of to the outside with parentheses And the parentheses go through the bond. So we're not saying there's extra atoms here on the ends of these bonds. We're just saying that's showing that the end of this one is meant to connect to the beginning again of the next one. And then we can specify a number down here in the subscript. If we wanted, let's say, 100 units, we would say 100. But if we're just trying to express the polymer in general, we use an n to just say some number. This is going to repeat some number of times. Okay. So to come to this, or you could also do it in the condensed structure form, which might look like this. To get to this, sometimes it's easiest to first kind of draw it out in a bigger way, then find the part that's repeating, and then do that. The other kind of shortcut to finding that polymer structure is to look at the monomer and just take away the double bond or one of the multiple bonds and then show it extending from both sides. There are broadly two classes of polymers that we're going to look at. The polyethylene is an addition polymer. Sometimes called a chain growth polymer. And an addition polymer generally starts with a double bond, although it can also be a triple bond. And there could be other stuff attached. We're going to see some more examples, and you'll kind of see what I mean. And then that thing just connects over and over again. So for example, polyethylene, we start with our 2 carbons, and we just kind of connect them over and over again. The second type of polymer that we're going to look at is called a condensation polymer, also known as step growth. And that word condensation means that we're going to lose water to connect. If you remember back to when we were talking about the macronutrient structures, the lipid structures, the carbohydrate structures, we looked at, and proteins, we looked at condensation reactions that we also call dehydration reactions, where water goes away and then what's left over is connected. And so you can make polymers like that too. In fact, a protein is really a condensation polymer of amino acids that are repeating over and over again. A starch is a condensation polymer of monosaccharides that are connected over and over again. So we'll look at those in a little bit. You'll see some examples. Let's continue with some other addition polymers so you can get a sense of how to draw these things and how to figure out what those structures are supposed to look like. So we've got, similar to polyethylene, we could start with a pretty similar molecule called propylene. And we can make polypropylene. Now let's think about how we do this. So the difference here is now we have a third carbon. And so the question becomes, well, how do we make the chain? Is it just going to extend from here, like from the left side and the right side? Because really that would make the same thing as polyethylene. You just have this long chain of carbons. That's not how this connects. Remember that those connecting, the things that do the connecting are the carbons that were a part of that double bond, because it's those electrons from the double bond that are now kind of spread out and need to be connected that way. So our connections are the same as with polyethylene. So we can look at 1 and 2 here. And that's where the connections are going to come off from. So every 2 carbons in the polymer are going to have a CH3 also connected to them. So let's draw that and see what it looks like. So I'm going to take my 2 carbons, my CH and CH2, And again, that's what we labeled as carbon 1 and 2. We get rid of that double bond, and then we connect these to other examples of themselves. And we're not breaking any other bonds. So the CH3 that was connected to carbon 1 still has to be connected. All right, so now this is our repeat unit, and this is just going to happen again. So we've got another 2 carbons from polypropylene with the CH3 coming off that first one. And it's just going to be repeating over and over and over again. So this is polypropylene. And if we want to draw polypropylene in the smallest repeat unit structure, we can go like this. With those parentheses and the N, just showing that that's the thing that's going to repeat over and over again to make this polymer. In a line structure, we have a similar thing. So we're going to have our 2 carbons inside the parentheses. And then 1 more carbon coming off of that first one. So that's what a line structure would look like for polypropylene. And if we were to draw that out in a longer chain, just so you can kind of see what it might look like. So you'd have something like that. So where polyethylene is just a chain of carbon atoms, polypropylene is a chain of carbon atoms with an extra carbon hanging off every other one. Polypropylene is also a common polymer. It's particularly water resistant. It can't get kind of like soaked very easily. So things like ropes that are meant to be outside or meant to be inside the water are sometimes made of polypropylene. Food containers are made of polypropylene. So like the disposable, well, it's like semi-disposable ones that you get at restaurants or that you can just buy, like the Ziploc or Glad or whatever, and you put your food in it and it lasts a while and then you eventually can throw it out if you want to. Those are polypropylene. Polypropylene was really important for food containers when there was an issue with this molecule called BPA. That was in harder plastics like polycarbonates, like these kinds of things. But polypropylene never had those kinds of additives. Those were always food safe. So those kinds of containers are don't have those kinds of plasticizing additives, and that's why they're so useful. There's also clothing made of polypropylene. Some of the like moisture wicking type stuff is sometimes made of polypropylene. Although I think nylon and polyester is more common now, but I think you can still get polypropylene clothing in that way. All right, so that's pretty much how these things work, how these polymers work. There can be other things hanging off down here. They can hang off both carbons. Let's look at maybe a couple more examples. If we start from something that looks similar to polyethylene but has fluorine atoms instead, it's called tetrafluoroethylene. Then we can make a polymer called polytetrafluoroethylene. Polytetrafluoroethylene. I'm just going to write the abbreviation. So it's PTFE, which you may have seen. That's also known as Teflon. Teflon is like a brand name. You can get this material. It's known for its non-stick properties. It was actually kind of discovered by accident. Somebody in a lab had a big cylinder of this gas. This is a gas here. And they went to open it up to use the gas and nothing came out. But there was still lots of weight in the cylinder. So they actually cut the cylinder open and found this like chunk of stuff that had not corroded to the sides of the container at all. And so started investigating it for its non-stick properties. It turns out that these fluorine atoms make this extremely unreactive. So anytime when there's a chance of corrosion or stuff getting stuck to something, you can use this polymer to avoid that. So probably most famously, that's pans, those non-stick pans that you use to cook eggs or whatever, where stuff doesn't stick to them very well. But there are a lot of other important uses of PTFE, like in medical devices. If you're putting anything with a tube, like especially a thin tube, inside someone's body, like an insulin pump or something like that, you want to make sure that tube isn't going to get clogged. And so you can use a Teflon tubing that won't allow stuff to stick to the sides and get clogged. A lot of laboratory equipment uses that as well. You also see it in tape for plumbing connections that you wrap over like a metal screw-in connection, like a galvanized screw-in connection. And that's because that tape will prevent the metal from corroding together and getting stuck because nothing will react with this PTFE. If we want to draw this in line structures, we have to show the fluorines as well. So we have our 2 carbons, and then each one has 2 fluorines connected to it. And if you imagine those fluorines as, you know, balls like an atom shape, you can see how they kind of like protect everything and they stop it from being reactive. All right, another common addition polymer. If we put a benzene ring, which is this thing that we've seen a few times, on our ethylene, this molecule is styrene. And then if we polymerize that, we have polystyrene, which we can also draw a line structure like this. Right? So now instead of just a carbon hanging off there like in polypropylene, we have this whole benzene ring coming off here. Again, the parentheses are optional there. This is most famously known as styrofoam. So polystyrene, because of that benzene ring, it's actually a very rigid polymer, and it can hold a lot of air or any other gas. So when polystyrene is produced as styrofoam, they do this reaction while pumping in tons and tons of, I think, carbon dioxide, and or it might be some other gas, it might be air. I'm not really sure, but I think it's carbon dioxide. And that air gets trapped in the polystyrene polymer, and that's what makes a foam. One thing you can do if you have some styrofoam, you can put it in a solvent like acetone, and you'll actually see it won't really dissolve in the acetone, but the acetone will cause all the gas to escape. So you can take a big chunk of styrofoam or like a big styrofoam cup and put in a little bit of acetone, and it'll look like it's just kind of melting. It's not really melting, but all of that gas is being released, and all you're left with is a solid polystyrene. So polystyrene and these kind of plastic foams present this this interesting problem when it comes to waste and recycling, because something like styrofoam takes up a lot of room in a landfill. It takes up space because most of it is air or a gas. But because there's so little actual plastic being used, it's extremely easy and cheap and energy efficient to produce. So for example, a number of years ago, there was some movements to try to get rid of, I think they're still going on, try to get rid of styrofoam cups. You know, it could be quite different. All right, looks like we had a little interruption in the internet, so I'm gonna wait for it to catch up a second here. Okay, I think we're back. hopefully. All right, let's take a look at some condensation polymers now. So condensation polymers are a little bit more complicated to put together, to draw and all of that, because it's not just one little molecule that you just repeat over and over again. It's usually a couple molecules that are reacting with each other in these condensation reactions. So to review condensation reactions, they always are of the form R. I'm just using as like a wild, like, could be whatever. It's a common chemistry convention to just say R means like some molecule, some stuff. So you would have something that has a carbon double bond oxygen and either an oxygen or a nitrogen attached. We're going to look at both examples. Something like that. And then we've got an OH, an alcohol, connected to something else. So we'll call that R2, R1 and R2. And so in that condensation reaction, what happens is one of the oxygens and two of the hydrogens leaves to become water, and the remaining carbon connects to the other oxygen to make a new structure. So the new structure is these things connected together. Like that. All right, so this is review. So if this seems brand new to you, please go back and look at when we were talking about carbohydrates, lipids, and proteins, because we went through how to do all these types of reactions. So this would be like what happens in fats. When fatty acids, which is kind of like this molecule on the left, react with glycerol, kind of like this molecule on the right, to make glycerides, mono, di, and triglycerides. So that's called a condensation reaction. And the resulting molecule here is called an ester. So if you use this chemistry to produce polymers, then what you're making are called polyesters, which you've probably heard of. Polyester is a really, really common polymer. So let's look at a couple examples here of real world ones that are common. So this is perhaps the most common polyester out there. You take this molecule, which is called terephthalic acid. I'll write this out eventually, but I'm just going to talk about it for now. So this is terephthalic acid. And then you react that with ethylene glycol, which is this. And we're going to do that exact kind of a dehydration reaction. So we're going to take one of the oxygens and two of the hydrogens to make water. And we're going to connect what's left over. These molecules get big, so I need a lot of room. That's why I'm kind of just cramming it in the corner here. All right, notice I'm not changing anything else about the molecules. I'm just making this connection. So now I've got that O connected next to the C. All right, so now I've got this connection. So that's not a polymer yet. That's just a little bit bigger molecule. Those things reacted. But notice what happens here. This resulting molecule has this acid part on the left, and then it has this OH part on the right. So now this whole molecule could actually react with itself again and make something even bigger. And that's exactly what happens. So we can react this again on the other side. We're going to take this entire thing and put it over on this side again. And I'm going to have to like curve it down the bottom of my paper here. O CH2, CH2OH. So you see how that's starting to combine? And now this molecule also, again, has OH on this side and acid on this side. So we could do that again, and we could keep alternating between the terephthalic acid, which is this thing with the benzene and the 2 carbon double-bond oxygens, and the ethylene glycol. Terephthalic acid, ethylene glycol, and just kind of keep going over and over and over again until this thing makes this big polymer. Let me put this up so you can see it here. All right, so this keeps going on and on. So the connections here end up being from both sides. And this is known as polyethylene terephthalate, or PET, or sometimes PETE. So this is the most common polyester because this is what's used in bottles. So things like water bottles, pop bottles, juice bottles, all that kind of stuff, that's PETE. If you look at the bottom of a plastic container, you will often see a little triangle with a number in it. I don't know if you can see it on my water bottle here. I don't know if that's really coming through, but it's a little triangle with a 7. Now, confusingly, that triangle looks like a recycling symbol. Like that. Which makes you think, oh, this thing is recyclable, but that's actually not true. That symbol tells you what type of plastic it is from the number in here. So PETE is plastic number 1. So that one always has a number 1. But that does not actually mean it's recyclable. And from the real definition of recycling, which means something that you can melt down and reuse again in the same fashion, plastics are not recyclable. It's kind of contrary to what we're always told. Glass and aluminum are recyclable. You can melt down glass and make a new glass bottle. You can melt it again and make a new glass bottle over and over and over again. Same thing with aluminum. You can melt aluminum cans down and make new cans over and over and over and over again. But plastic, you can't. All you can do is what's called downcycle it. You can take it and you can make something else out of it that isn't quite as good anymore because the thing that you make out of it next can no longer be recycled. So for example, plastic bottles, you can make certain types of clothing out of them, like fleece clothing, because of the way that the fibers are reformed when they're melted back down again. But then that's it. You can't recycle it anymore. Then you got to throw it away. So it's not technically recyclable. It can be remade into something else, but not recyclable. And depending on your local regulations, many of the types of plastic are not even done in that way. So if you're throwing everything that sort of looks plasticky or that has this symbol in your recycling, you might be doing it wrong. Check your local waste company and see what types of things you can throw in there and what types you can't. Furthermore, any kind of contamination can really damage the recyclability of any of these materials. So like if you have a really dirty plastic container, or one example I see all the time is like a pizza box. Pizza box is cardboard, so we think, oh, cardboard, you can recycle cardboard. But if that cardboard is soaked in grease from the pizza, you can't recycle it anymore. So you got to just throw it away. If you put anything you put in your recycling that is contaminated like that, I think it's above 10%. If it's contaminated above 10%, it just has to get sorted out and thrown away, which is more work, more labor for the people doing the sorting at the recycling station. So what happens now is actually most of the stuff that we send for recycling, particularly plastics and stuff like that, don't really get recycled. The things that do get recycled that it's important to make sure that you recycle are aluminum cans and other types of aluminum and glass. Those can definitely be recycled and you save a lot of energy over trying to make those things from new. But plastics, not so much. Really more important to reuse plastics. So when you get like a container, if you get something in a plastic container, like, butter or, I don't know, sour cream, whatever it is you get from the store in a plastic container, you can just wash that out and reuse it for something else. All right, so let's look at one more type of condensation polymer known as polyamide. And that's what we get when, instead of having oxygen on the other side from that acid functionality, we have nitrogen. And some of these actually are in the same molecule. So let's take a look at this molecule. Which has an amine, an H2 on one side, and an acid on the other side. So this is really a lot like the amino acids we saw in the protein chapter, just with more carbons in between. And these molecules can polymerize in the same way that amino acids polymerize. So we can take this molecule, we can copy it, I'm gonna have to move this around a little bit. I probably should just redrawn it. That's okay. All right, I copied that molecule, and then I'm going to get rid of one of the hydrogens. So not both of them in this case, just one, because of we're only taking 2 hydrogens to make water. And then we're taking the oxygen and the other hydrogen there. Then we connect what's left. So that type of a bond, as we learned in the protein chapter, is known as an amide, or if it's proteins, it's peptides. But this is known as an amide bond. And so this type of a protein, or this type of a polymer, is known as a polyamide. And there are lots of different types of polyamides, but often the brand name is used, which is nylon. So if you hear about things made of nylon, there's lots of different kinds of nylon. You can imagine that why nylon is so customizable, because whatever you put in, whatever types of molecules you start with more carbons or fewer carbons, or you can have alternating, some more, some fewer, and that's going to affect the properties of the nylon fiber. So some can be extremely smooth, some can be extremely strong. Bulletproof fabrics like Kevlar are made of polyamides when you have benzene rings in the middle here that make it really, really rigid and strong. Nomex, which is a fire-resistant fabric, is made of polyamides as well. That's a nylon as well. And then, of course, a lot of our clothing is made of nylon. So you'll see that all over the place. Very strong, other types of very strong, like technical fabrics, like Cordura, canvas replacements, things like that, are made of nylons with various types of molecules in here, or of parts in here, that make it extremely, extremely strong. All right, so that's the basics of polymer chemistry and polymer structure. So what I want you to be able to do from that is a couple things. So one, I want you to be comfortable with drawing these structures. Like if I give you a monomer, you should be able to draw the polymer. Now, functionally, that's not really going to happen in the quiz because it's on Blackboard. There's no structure drawing program in Blackboard, so it's more about identification. So if I draw you a monomer, can you identify what the polymer is that it would form? And then vice versa. If I draw a polymer or show you a structure of a polymer, what is the monomer that it came from? And then the second part that I have up here is to do this polymer identification to give you a better sense of the physical properties of polymers. So you're going to look around for some plastic materials, which are generally polymeric materials, and these can be like a bottle or whatever. And then you're going to try to come up with a plan to identify the polymer. And this is something that's often done because if you just have some piece of plastic, not necessarily easy to tell what kind of a plastic it is, what kind of a polymer it really is. And let's say you want to make a replacement part, or you want to make sure that the replacement has the same properties or whatever, then you have to identify it. So sometimes that's fairly easy. If you have a little symbol on the bottom, you can look up that symbol and at least get a guess. But even if you do have that, I want you to do to propose some tests of how you would figure that out. Now, we would normally do this in lab. Because you're at home, I can't ask you to actually physically do the tests because a lot of them include heating to fairly dangerous temperatures. And when you heat plastics, they tend to give off nasty stuff. So if you melt, like, that's why we don't have any like home, or one reason why we don't have home recycling stuff for plastics is when you melt down plastics, they emit pretty dangerous gases. And without proper ventilation controls, you don't want to be breathing that stuff in. So it's not a good idea ever to set plastic on fire or to burn it or melt it, particularly indoors, because they can give off some pretty nasty odors. So there's also some chemical tests in here. And so I'm not asking you to do these tests. I'm asking you to propose them and say, how would this test tell you what kind of a polymer you have? So I have an example here. So like one test is to heat to 190 degrees C. Why did I pick that? Well, I picked that because I looked at this. Oh, actually, it's not in this document, but I looked up melting points of polymers. You can look up a table of melting points in polymers. And I picked a temperature that would differentiate these from these. Now, this isn't enough to identify it because heating to that only tells me that it's one of these two. If it melts, it's one of those two. If it doesn't melt, it's one of those two. So assuming that I've narrowed it down already from some other stuff. But maybe heating at different stages, I'll be able to tell exactly what the polymer is. Or maybe I can heat it and then I can look at the density, which is also known as the specific gravity. So if I, or solubility, here's another example. So here's a table that tells you what different polymers are soluble in. So let's say I'm looking at polyethylene versus ABS, which is Legos plastic. So LDPE, HDPE, that's low density polyethylene, high density polyethylene, right? So I can see that in all of these solvents, my ABS plastic will dissolve, but my polyethylene plastic should not. So if I have an unknown sample of plastic and I try to dissolve it in, let's say, acetone, then if it dissolves, I know it's not polyethylene. I know it's going to be one of the other ones that does dissolve, or like gasoline. Please don't try to dissolve things in gasoline. Don't play with gasoline. Not good. So that's how that's one way you can determine them. You could also look at specific gravity, which is also known as density. It's not exactly the same, but for our purposes, we can think of it that way. So we could look at, for example, polyethylene versus polypropylene, right? Polyethylene has a higher density, high density polyethylene has a little bit higher density than polypropylene. So that might be a way to tell those apart. So that's the idea. It doesn't have to be perfect, and I don't want you to actually do it, but I just want you to think about how you can identify what an unknown polymer sample might be, and then how you can do some physical tests to confirm that. All right. So if there's any questions on this, let me know. Otherwise, I will see you again on Monday. I look forward to seeing your polymer identifications. Bye, everybody.